All right, how's everybody doing? So I thought since we missed class, what I would do is record a little video of what I was hoping to actually get through in class so we don't actually get much further behind, and then we can actually kind of move on to chapter 2 by the next class. So you should have the handout for this so you can actually work on the handout as extra practice in addition to the actual homework. But in section 1.5, the goal was we want to cover inverse functions. So last time we had talked about composition of functions, and inverse functions are related in the sense that if you take the composition of a function and its inverse, it gives you just x back again. I think I had mentioned that in class. So just as kind of motivation for like what is an inverse function. So again, let me go back to my little sketch drawing that I like to talk about for functions. So the idea is if this is the domain of f, and I take some x value and apply f to it, then I know I land on some f of x over here, which of course is in the range of f. So an inverse operation, what its goal is to try to undo that original operation. So the idea is what I want to do is actually start over here and be able to take that map and run it back the other way. So this reverse map is actually what's called f inverse, or the inverse map. So this is actually read as f inverse. And again, it's the inverse map of f. It undoes f. So notice f inverse actually starts over here, which means that the range of f is actually the same thing as the domain of f inverse, and f inverse actually ends over here, which means the range of f inverse is actually the same thing as the domain of f. So that's important because the idea is if I know the domain of and range of f, technically I know the domain and range of f inverse because they're just opposites of each other, which is kind of cool. All right. So the idea is like, if you take some x value, it gets mapped to some y value in the range. Well, that y value is now the input for f inverse, and the idea is we want to map it back to that x value from the original domain. So kind of a quick example using just like a table of values to help us kind of decide like what f and f inverse looks like. So let's assume our function is defined by the following table. This is our f of x function. And so the goal is, what if I wanted to write down what f inverse looked like as a table? So remember, the idea is that this is of course the domain for f, and this is of course the range for f. So remember, the inverse does the flip of those guys. So this second column is actually going to be the domain for f inverse, and this first column is actually going to be the range of f inverse of x. So the idea is I actually want to kind of think of it as going backwards like this. Or another way to think about it is I'm actually flipping the ordered pairs. So the ordered pairs for f of x were 1, 2, 2, 4, 3, 6, 4, 8. So the ordered pairs for f inverse are going to be 2, 1, 4, 2, 6, 3, 8, 4. It's going to be the total flip. So in this case, my new table should have domain values 2, 4, 6, and 8. And it should have range values of 1, 2, 3, and 4. So the idea is, in order to find the inverse, what we want to do is actually flip the x and y coordinates. So that's actually the goal in general if we're actually trying to do this algebraically. So let's say we wanted to find the inverse. Oops. Of f of x equals 4x plus 5, say, for example. Well, that same technique that we used with the table is the exact same technique that we want to use algebraically. So the idea is we want to actually flip-flop these x and y values, but instead of doing it with individual numbers in ordered pairs, we want to do it in general. So first, rewrite f of x equals 4x plus 5 as y equals 4x plus 5. So it looks more like an ordered pair. Now second, switch the x's and the y's. So what we should have is x equals 4y plus 5. So again, just flip-flop the x's and the y's. Now last, solve for y to find our f inverse of x. So now we just want to do algebra to actually get the y by itself. So in this case, we've got x equals 4y plus 5. So to get y by itself, we'd want to subtract 5 from both sides. So x minus 5 equals 4y. Divide both sides by 4. And we see that y equals x minus 5 over 4, which is our f inverse of x. So that's how we find the inverse of a function. Alright, so let's try another one. This one's a little bit trickier, because this book does like to be tricky sometimes. So let's find the inverse of f of x equals x plus 3 divided by x minus 2. Alright, so that seems a little bit worse because it has multiple x's in it, but we still want to do the exact same thing. So first, replace f of x by y. So y equals x plus 3 all divided by x minus 2. Second, replace all the x's by y's, replace all the y's by x's. So we've got x equals y plus 3 all divided by y minus 2. So lastly, we want to solve for y. Now in this case, since we have multiple y's, we're going to have to at some point in time get all the y's together, and combine like terms and things like that. So the first thing we want to do in a situation with these fractions is actually think of x as being x over 1 equals y plus 3 over y minus 2, and cross multiply to actually clear the fractions out. So if we cross multiply, we're going to get x times parentheses y minus 2 equals, well, 1 times y plus 3 is just y plus 3, so that's okay. Now we've got all the fractions are gone, so eventually we just want to get all the y's to one side, but first we have to distribute this x inside. So xy minus 2x equals y plus 3. So now I've got a y there and a y there, so I want to bring those guys all to the same side. So let's go ahead and say subtract y from both sides. So I'll kill those y's off. So writing it out, I've got xy minus y minus 2x equals 3. So now I need to get rid of that negative 2x, so we can do that by adding 2x to both sides. So that gives me xy minus y equals 2x plus 3. So now the idea is everything on the left contains a y. So what we want to do is actually factor that y out so we can solve for y. So if I factor a y out on the left, I'm left with x minus 1 all equals 2x plus 3. So finally, the last step, let's get rid of the x minus 1 by dividing both sides by x minus 1. And so our inverse function is going to be 2x plus 3 all over x minus 1, or f inverse of x equals 2x plus 3 all over x minus 1. All right. Is that okay? A little tricky. It's got a few extra steps in it. Now there's a good challenge problem, 1C. It's related to the one we were just working on, so I'll leave that one for you guys to work on. But if you get stuck and you want to see it, you could always ask, and I can make up a little video to go along with that guy as well. All right. So one other thing is, let's talk about the domain and range of f, the domain and range of f inverse, and finding a formula for that guy. So again, let's look at an example. So what we're going to do is find the domain of f, the range of f, domain of f inverse, and the range of f inverse, and the formula for f inverse. So let's look at the function f of x equals x plus 3 all over x minus 5. So we've got to have one that has a bad spot, otherwise it won't be all that exciting. So one way that we can actually find this guy, like the domain for f, is going to be pretty straightforward. So again, remember, to find the domain of a rational function, what we want to do is we want to focus on the denominator, set it equal to 0 to find any bad spots, and then just throw out those bad spots. So in this case, when we add 5 to both sides, we see that x equals 5 is our only bad spot. So as far as our domain, anything but 5 is actually going to be okay. So in this case, our domain of f of x is going to go from negative infinity to 5 union 5 to infinity. Now the range is actually, this is kind of a weird section to put this, because to find the range of this function the way it stands, what we have to do is actually know a little something about horizontal asymptotes and things like that, which the book doesn't actually cover until later. So what I'm actually going to do instead is use the fact that if we can find the domain of f inverse, which will look similar to this guy, that will actually allow us to find the range of f and vice versa. Because what we've found so far is, now that we know the domain of f of x, we also get for free the range of f inverse of x. Because remember, these guys are related. So I know the range is also going to go from negative infinity to 5, union 5 to infinity. So what I'm going to do is actually find f inverse, algebraically like we did in the last problem, and then find its domain using the same technique we did here, and now allow us to get the range of f for free. So let's find f of x, f inverse. So first, replace f of x by y. So we get x plus 3 over x minus 5. Replace the y by x, y's by x's, x's by y's. So x equals y plus 3 all over y minus 5. And now again, solve for y. So again, this is exactly like the problem we did last time. So we want to let x be x over 1 equal to y plus 3 over y minus 5. Cross multiply is the first step to get rid of the fraction. So we get x times y minus 5 equals is y plus 3. Again, bring the x inside, so we get rid of the parentheses. So xy minus 5x equals y plus 3. Again, bring all the y's to one side. So subtract y. So xy minus y minus 5x equals 3. Add the 5x to both sides. So we have xy minus y plus 5x plus 3. So again, factor out the y. So it gives us y times x minus 1 plus 5x plus 3 divided by x minus 1. And lo and behold, there's our inverse function, which is going to be the 5x plus 3 all over x minus 1. So since that's a nice rational function, we can find the domain of f inverse of x exactly the same way. Set this denominator equal to 0 and solve for x. And gives us x equals 1, which again is our bad spot. So what we see is that the domain of f inverse of x is going to be from negative infinity to 1, union 1 to infinity. But again, since the f inverse and f are related, we also get for free the range of f of x is also going to be negative infinity to 1, union 1 to infinity. And lo and behold, that gives us a way to find both the domain of f and the range of f, domain of f inverse and the range of f inverse, along with a little practice, again, finding an inverse of a weird rational function. All right, so kind of the last thing, just to sort of, notice, you may ask the question, does every function actually have an inverse? So does every function have an inverse? Oops, sorry. And so the answer is no, it doesn't. And so what allows us to have an inverse is, so think about the way these inverses work. So remember, the idea is that what we're doing is we're letting the output values now become the input values. And remember, what makes a function work is that each x value is associated with just one and only one y value. So a function, each x value is associated with one and only one output value. So in other words, each x gets sent to one y. So if we're flipping around and y's are now the input, in order for f inverse to be a function, each y needs to be sent to one and only one x value. So in other words, you can't have, like, if you look at your y column, you can't have like 3 a bunch of times. Like every y column, every value in the y column has to be distinct. There can be no repeated numbers in the y column. No repeated numbers. On a table, for example. So from a graphing perspective, what we're trying to show is we don't want something like this to happen, basically. Because the idea, if I have something that looks like that, it makes a function fine, because if I draw vertical lines, I'm never going to cross the graph in more than one place, which is perfectly fine for something to be a function. But for something to have an inverse, what we have is what's called the horizontal line test. And so the idea is, if a horizontal line crosses the graph in more than one spot, so if the horizontal line crosses a graph in more than one spot, the function has no inverse. So this function, of course, is bad, because no matter where I draw a horizontal line, I'm going to cross the graph in more than one spot. So this is bad. No inverse. So what I need for something to be invertible would be something like a straight line. That's actually good, because of a straight line, no matter how many horizontal lines I draw, I'm never going to cross the graph in more than one spot. It doesn't always have to be straight. It can have like a little bend to it, as long as it doesn't kind of curve back on itself. So this guy would be good. So this one's good. This one's good. So what we need is we need the function to be increasing all the time. That's the characteristic that's actually happening in these two good graphs. So the function should be increasing, which means the y values just keep getting bigger and bigger and bigger and bigger forever and ever and ever. The function should be increasing all the time. If your function's increasing, it'll have an inverse, and then we can do what we did before to actually find it. So hopefully this video helps. Like I said, definitely try the homework problem, try the practice sheet that you actually have already. If you have any questions, email me and let me know. Otherwise, hopefully I'll see you guys in class on Thursday. So take it easy. Good luck.